Apple has the best advantage because they're probably the only ones who realize that they haven't locked it down. I think Microsoft, I think Meta, I think Google, all think that they're like the winners at this point. Mm-hmm. And you see this all the time. The folks who are the most behind sometimes end up getting ahead of everyone else.
Hello, fellow data nerds. My guest today is Jonathan Ross. Jonathan is the founder and CEO of Groq, a company that develops high-performance microchips purpose-built for AI and machine learning. Prior to founding Groq, Jonathan invented Google's AI processor, the TPU. Jonathan, welcome to World of DaaS.
Thanks for having me. I appreciate being here.
Now, I'm really excited. Now, you have some really interesting ideas about data, compute, and the idea that kind of we're transitioning from an information age to a generative age. What does that mean, and what does that mean for data?
So we transitioned into the information age when, for the first time, we're able to make high-fidelity copies of data and distribute them throughout the world. And over time, that changed the way that we did business. All of a sudden, it went from being about who had the answer in the moment to who came up with the answer. There was like the origination of the idea as a concept and as a monetizable thing. And we got new technologies over time. We got the internet, which was about making high fidelity copies and distributing them instantly. We got mobile, which was about doing it in your hands, right? But really, these technologies were the same as the printing press. They were just much better. And that degree of change was enough to break all of our intuition to some degree. Generative AI is not an information age technology. It's not about taking copies of data and distributing them. It's about creating things in the moment. It's creative. It's generative.
Yep.
And you're going to get an answer in the moment that is custom to you. And that requires compute. So that changes the paradigm and it breaks all of our intuition. Instead of it being about who has the data, it's who has the compute, who can create the answer for you right now.
And does that mean data is less valuable than before and compute is more valuable? Or how do you see
it's stacked. It's you can't have the models without data.
Yeah.
But you also can't have an information age economy without energy, right? And the industrial age was really based on energy. And so what we have is this new stacking, but it does change the paradigm a bit. Oftentimes when we're talking to people, they talk like it's so funny because it's almost the more sophisticated someone is, the more entrenched this idea about being close to data is. When you and I first met, did I show you the demo at all of what we had?
Yeah, I think so.
Yeah. And we were like 9,000 miles away, 8,000, some number of thousands of miles away from where the servers were, and it was almost instant. And so if you think about it, the number one export of India is tokens. They're just generated by human beings as opposed to generated by a computer. And you don't need locality because you have a small amount of data coming in. You have an enormous amount of compute producing an answer, and then you send a small amount of data back. So oftentimes we'll get 2 bytes, perform 180 billion operations, and then send 2 bytes back.
Yeah. Like a customer service agent or something like that.
Exactly. So we don't even put hard drives in our servers. We just completely decouple, and we're just focused on the compute. And data is incredibly important. It's just not what we do. We're doing this generative age thing, but we build on top of the work of others who do things in data.
Got it. But like, if we're just talking about it again, like less talking about our own book, more talking about like where the world is going here. In the world that it's going, like, what is this transition going to generally look like, and what does it mean for like the different, where there's a data provider, there's a compute, there's obviously like the bandwidth stuff, there's the energy, like where do all these things kind of like stack up, and how will they vis-a-vis one another, how will the power shift?
Well, the power will shift in one way, which is historically you had a lot of power just because of your geographic location, and literally you could pull oil out of the ground. And then we started building data centers, and a shift there was where you build the data center gives you some power. It's not just where you find the resources, but where you build it. And then compute
Why
actually,
is that? Why would Oregon have more power than Nebraska or something?
Hello, fellow data nerds. If you're enjoying this episode, please hit that subscribe button. I would super appreciate you being a subscriber to World of DaaS. Now, back to the episode.
well, in Oregon's case, I don't know that they do have more power, but if they did, it's probably because they have a lot of hydropower.
Well, I'm sorry, I mean like actual, but like why is
So
it like you said somebody has more
I,
power because the data center is
I
closer
mean,
and stuff?
I
Yeah,
mean more technologically. So think about it this way.
yeah,
Right now, there's a conflict between the U.S. and China, and that conflict is about largely getting access to many technologies, but in particular AI compute. And there's a strength leads to strength aspect here, which is with things like oil, being better at pulling oil out of the ground doesn't give you more oil to pull out of the ground, right? It doesn't have this cycle where the more
right.
oil you pull out, the more oil you get. But with AI and these sorts of technologies, the better you get at it, the more you're able to get better at it.
Yep.
And so you could actually pull away from others. And so there's a bit of a race right now to see who can actually get a lead on this. But whoever has the initial lead could potentially pull away far enough that it'd be hard for others to catch up.
But in this thing that there's this compute side, where there's the chip side of it. There's like, let's say, for better lack of a better word, like the algorithmic side. This would be like an OpenAI or some of these Anthropic type of models. There's other types of things like is it like every single piece of the ecosystem is equally as important, or do you think some are more important than others?
If you're missing some of it, you may not be able to get all of it, but some of these pieces are going to be just given away for free. For example,
God, so it's just open source. We'll have an open source. Yeah.
Open source models in particular. And if you think about it, Linux won when it had enormous headwinds. People did not believe in open source at the time of Linux.
Yeah.
Linux had to prove it. Now open source is considered the de facto way that things will end up going for most projects like this. And many of the people that we speak with are just operating on the assumption that eventually an open source model will win. And the question is, which one?
One of the reasons like Linux really started taking off in the aftermath of the .com crash. So like kind of prior, everyone was buying Sun, and they were like very happy with paying just like extraordinary amounts for those Sun boxes. And then, the Linux box was like 10 times cheaper or something, right? Than the Sun box. And because like all of a sudden they had to like money was important and they had to save costs, Linux started taking off. Is that like a moment that people are going to start thinking about here, or how do you think about that?
Interesting. So probably one difference here was the rate of adoption for the early internet stuff was much lower than the rate of adoption for generative AI. I mean, it's really only been a year or so. And think about how much has been like the rate of growth of companies
It's crazy.
doing this.
Yeah.
Yeah, it's very different. And what you're seeing is people are already starting to care about things like, is this a good product? Which wasn't really for the early internet. It was, well, this is the internet provider that I can get access to.
Yeah.
I'm going to use, Uncle Bob Serve, right? Didn't really like your local ISP. No one really like it was the only one you had. This is the one website I know to go to this thing. And now what you're seeing is there's really a focus on who's going to be the winners. And so if you have a much better approach, people tend to flock to it now.
Yeah. That makes sense.
So cost. No one wants to get stuck in something proprietary. This is one of the big ones that we hear. And also the just assumption that open source is going to move faster because that's what people have seen in the past. And so you don't want to be on some proprietary thing, which, yeah, it's ahead right now, but open source is going to pull ahead.
As we move from this like compute driven, as we move to this kind of compute driven generative age, like what are both the societal and economic implications are going to happen?
Oh man. Uh, so I can't predict what will happen, but there are a couple of things that we've noticed, which are in the entire point of going into a different age and why you would call it a different technological age is it breaks all of our intuitions.
Yeah.
And one of the most interesting ones that I think is completely broken is we keep thinking of each technology as displacing work. One of the things that's probably going to happen is we will probably create more jobs for people than we have people. There will suddenly be a lack of supply of people to do things. And I'll give you a concrete example. It used to be that no one would have a graphic in in their articles, their random news articles. But now it's so easy to create one. Most articles have some sort of graphic,
Yeah.
right? Most blog posts have an article,
For sure. Yeah.
and people probably spend more hours in overall as human beings generating these because it is so easy to generate them. And this is called Jevons paradox. And this was noticed in the 1860s by someone writing a treatise on coal, where what he realized was every time steam engines got more efficient, uh, um, rather than buying less coal, people bought more coal. So
Yeah.
steam engines get more. Why are they buying more coal? Well, OPEX goes down, more things go into the money, people do more things, right? And so what will probably happen is with most of the things that generative AI makes easy, you will actually see an increase in human activity on that. And there's always going to be someone who's going to be more entrepreneurial and figure out a way to monetize that, get a whole bunch of people working on it. So I expect the number.
I haven't heard of Jevons paradox before. Is that kind of like a similar thing? Could be in for the layman might be like, okay, they made the highway from 2 lanes to 3, but the traffic is still just as bad because more people drive on it. Or
That's a good way to think of it. Yeah. Or price
okay.
elasticity is another way to say it.
Yeah, price. Okay, got it. That makes sense. And in this kind of new world, like what if you had a bet on companies, like what types of companies do you think have the biggest advantages and in this kind of more future world?
I'm going to shift that one a little bit. I'm going to
Sure.
say there are going to be companies that are definitely going to be successful in this. And then there's going to be companies that might be, and it's going to be almost impossible to predict who, but they might be even more successful than those other companies. When the information age came along, it was a great time to be in material production for paper. Now, which newspapers were going to succeed? I don't know. Don't know how that works yet, right? So this is a picks and shovels thing where we know we're going to need energy. We know that we're going to need, we know we'll need more data, right? That's going to be a thing. But we're also going to need more compute. But these are the picks and shovels of it. Then there's going to be which generative AI company is going to be the next Google, which one's going to be the next Microsoft.
But let's say we in, I don't know, airlines or something. Is it just like some airlines are going to do super well and some airlines are not going to do well because some airlines will adopt it faster than others? Or do you think like all airlines get wiped out or all airlines do better?
And you don't literally mean airlines. You mean
exactly. It could be anything, healthcare, trucking. Just go down your list of whatever industry that's it.
I will say this much: every single industry will be disrupted by generative AI. We've never had a technology that allowed us to,
and more. You think faster than the information age?
Much.
It will disrupt. Okay.
Much because there was a recent study where doctors competed against AIs to make diagnoses. And the fascinating part about this was you're not going to be too surprised if I say the AI outperformed the human being given the same data. So we're probably going to see AI involved in sort of diagnostic medicine. I just don't see how that doesn't happen. And ironically, it'll be a little slower for surgery, even though we already have robots for surgery. But diagnoses, you could just feed the data. It could already do better. The shocking part was when they paired a human doctor with the AI, the results were worse than just having the AI give a diagnosis.
And this is true in chess too, right? It used to be a human with the AI was better than the AI, and then very quickly the AI was clearly better than the human plus the AI because the human would like overrule it and stuff.
Yeah, and what I expect is we'll get to a point where medicine becomes so consistent that if you go in and you don't get a common issue treated, that will be malpractice, as opposed to you just did something egregiously wrong.
Yeah, yeah. Interesting. What about things like law enforcement and national security? Like, how will this generative world play there?
Let me start with the national security part. So there's a concept of first, second, and third offset. And a lot of people refer to the first offset as when gunpowder was invented. It totally changed the way war was done. The second offset was nuclear, because totally changed the way that conflicts were done. And a lot of people are now saying that AI is probably going to be the third offset. And it again, intuition is totally different. Instead of it being, so with nuclear, if one actor has a small number of weapons, you want to avoid that conflict at all costs. And so it actually, while it increased some risk for the species as a whole, it decreased the risk of conflicts happening.
At least major conflicts. Yeah.
Major
You'll have
conflicts.
like proxy conflicts like Vietnam or something happening.
Exactly, yeah. Right. It forced these conflicts to be smaller and more, it's not really me, but it's me, right?
Yeah.
With AI, the cost to launch a sort of AI attack of disinformation or these sorts of things is so low that you're probably going to see an escalation. And this changes the dynamic. And what you're going to need to be successful is not some amount of AI capacity. You're going to need AI superiority, like you need air superiority. And whoever has AI superiority will be in a very good position. If one entity has a third of the AI capacity of another, they will probably be in conflicts all the time. You're going to have to just dramatically overwhelm any sort of adversary.
But in a world where potentially, like, even if the U.S. has better offense, it may have more vectors of attack, which means it would have to have like significantly better defense, right? Or how do you think about that? In a nuclear war, like, I don't know, the U.S. doesn't have necessarily any worse vectors of attack than anybody else. Everyone is vulnerable. But in an AI war, like, it seems like the U.S. is more vulnerable to attack.
I'm particularly concerned about elections. My philosophy is all the concerns that we have about AI, as long as we get the elections to work and remain free and not in, like, we don't allow foreign money in elections. Why would we allow foreign compute?
Yeah.
And if we can preserve the elections, that'll give us time to fix the things that we discover are issues with AI in time. But that is the most concerning piece of our infrastructure. It's the elections.
Now, before we get into like all the new paradigms that you're working on, kind of like a lot of pretty much anyone who's listening to this is like probably well aware that NVIDIA has been this incredibly successful company. Why have these like GPUs like from NVIDIA been so successful over the last decade?
Yeah, there's a lot of reasons. First of all, let's go back a little bit in time, and let's talk about why CPUs became successful. The company Intel, most people have heard of. Intel originally was a memory company, and they begrudgingly switched to CPUs. And CPUs became a much better moneymaker. And the reason is CPUs fit into, they're not a standard. And so switching costs are higher. And it has all of the, if you've ever heard of the framework from Hamilton Helmer called 7 powers.
Yeah.
CPUs are like the personification of that. And then you see Intel, even with the Intel Inside going branding, all this other stuff.
Because they were both harder to copy, not a commodity like the memory
you couldn't swap
types of things.
Yeah, you like.
AMD had a x86 chip that was, I think, pretty similar, right? But was it just because it was just like it cost $2 billion to create a plant to go do, or what was the reasoning why the power was so high for like an Intel?
Well, with AMD, so there's another aspect here, which is when you're putting a chip into, when you're deploying a chip, it's not the cost of the chip that matters, it's the cost of all the infrastructure. So if you can increase the performance of a chip, the CPU, 15%, that effectively gives you 15% more value of the power that you're sending in, of the concrete in the data center floor, of the racks, of every single part of it gets 15% more economical. And so that means that a small performance advantage makes an absolutely huge difference in terms of your outcomes. And what you would see is a lot of the data center providers would build a system with AMD chips just to try and price negotiate with Intel with no intention of ever deploying them at volume.
Because the Intel chips were, even though so the AMDs weren't really copies, the Intel chips were just better. They were priced higher, but they were better.
Correct. And this was a strength leads to strength kind of thing. When you pulled ahead, you got an advantage. But there was also a double-sided market because you would write code for x86, and then people would buy x86 systems to run that code. And then there was all these bugs in x86, and that became a feature because eventually all the software had to support these weird bugs, and AMD had to copy the bugs of Intel. And
yeah, totally. Okay.
There were literally people who were experts in the bugs in x86 just to make sure that people could make copies efficiently. Now, with NVIDIA, what NVIDIA did very well was there's probably at least two major things, but then there's a bunch of other things around it. The first was CUDA was a double-sided market, very much in the same way, because there's no known algorithm today to automatically compile stuff down to GPUs.
And not everyone listening to this probably understands what CUDA is. So can you explain it for a relatively smart person?
So there's what CUDA is advertised as, and then there's what it really is.
Okay.
So CUDA is advertised as the development platform that you use to write code for NVIDIA chips. That is trivial to replicate. That has basically zero value. You've seen one.
Oh, I didn't realize that. So anyone could just create a new something else to go do that.
Yeah, that's the easiest thing in the world. In fact, this is one of the things that eroded the x86 Intel dominance was things like .NET, LLVM, Java, which sort of Java was a little more brute force. You had to get people to target it.
Yeah.
But these other things, your C++ would compile to it, and all of a sudden the switching costs went down in the Hamilton.
Yeah, because it would work with anything. Okay.
Yeah. but the same is true of like the actual CUDA programming languages. Those are trivial to re-implement. The hard part is what's called CUDA kernels. And what a CUDA kernel is if I write a program, like let's say I create a video game.
Yeah.
And I want that to run well on a GPU. The problem with that is there is no known algorithm to take that code and to get it to work on a multi-core system efficiently. So human beings write these kernels based on the code that you wrote. So if you're a major video game design studio, you send your game over to NVIDIA and they will write some kernels, and then they're in the driver. And when someone loads up that video game, it runs faster. It's just like someone writing assembly to make a C++ program run faster. Now, this is needed because of the multi-core nature. And this is viewed as a huge advantage by NVIDIA. And when we did TensorFlow at Google, we ourselves had to write the kernels for NVIDIA's GPUs. Otherwise, TensorFlow wouldn't have been relevant.
Yep.
And so it's got this double-sided market feeling to it that makes it almost impenetrable. And so that's one. The second is that NVIDIA has forward integrated beyond what most people have noticed. So typically, most companies, they'll build a chip, they'll build a system, they'll build networking, they'll do some software. They don't do all of them. And what NVIDIA did was they started with the GPU and CUDA, so the software, whereas AMD was more letting other people write the software for them. And then they added a system, the whole DGX boxes. Then they bought Mellanox to bring in networking.
Yep.
And now they're doing their own cloud to compete directly with their customers, right? And that's the thing. They've always forward integrated. So there was actually a recent, I forget which company it was. There was a company that made NVIDIA graphic cards for a very long time. 80% of their revenue or some large number like that came from selling NVIDIA cards. And one day they just announced, we're done. We give up. NVIDIA has made it impossible for us. They've squeezed out all of our margin. They make their own cards. We give up. Even though it's 80% of our business, we're leaving it. And so what they do is they just forward integrate. And every time they get something established, then they start forward integrating into the next part.
But they still are a big like TSMC customer.
Yeah, absolutely. And that would be going the other way. They tend to forward integrate. They don't tend to go back into their vendors, right?
Yeah.
They take what their customers do and they do that themselves. And that and there's a reason why they go that direction rather than the other direction, which is there's more margin the more up the stack you go.
Yeah.
And they're trying to capture more and more of that margin for themselves.
Yeah. Instead of like selling NVIDIA systems to other people who then rent them out, they could just rent them out themselves.
Yeah, I mean, that's what they're starting to do. And they just announced an inference service. So they're even going to go beyond that and start selling, I guess, token as a service and compete with all their token as a service customers. So, when you get to that level of power, people can't really say, hey, I'm going to drop you because you're going to compete with me. They're like, I have no choice. I got to keep buying this. And every dollar that they send to NVIDIA is just used to develop more R&D to replace them.
And they're clearly the biggest GPU customer. And obviously the only way to really kind of compete is with a new paradigm. You're working on this LPU. Mm-hmm. Like, what is different about that? And why is that important in this kind of more generative world?
Well, we really did those two things very differently that GPUs do. For one, we spent the first 6 months working on our compiler. So by the time that we started designing our chip, we already had the software working. And we were able to avoid the whole kernel issue altogether because it's just a completely automated compile. The second thing was we really built with all of that stuff, all the networking, the system, all from the beginning. So when we are running an LLM on our hardware, we're actually running on hundreds or thousands of chips, hundreds or thousands of our LPUs, not one or two or eight or whatever like you do with GPUs. And we can do that because we have our own integrated interconnect that allows us to scale up to more chips. And it's completely synchronous, which means it's sort of like, just imagine that you have a whole bunch of meetings scheduled. And that allows you to have a fairly efficient day where you're meeting with a whole bunch of people. Imagine if you couldn't schedule meetings. Imagine if you were trying to meet with a whole bunch of people and you couldn't schedule a meeting. That's the way it works inside of a CPU, a GPU, or any other architecture. We have the scheduling, but we had to do the interconnect, the networking to be scheduled as well. We had to do the drivers. We had to do the compiler. We had to do everything from scratch. And that was
because you're kind of like going between all these chips, like there's a need for this like super low latency, right?
Correct. And that's really the key. When you're running training, you don't need low latency. Training, you're going to finish in a month. All that matters is that you keep the hardware busy.
Yeah. Okay.
But with inference, It's very different. It's about how quickly you can give an answer. And that means that everything needs to be scheduled because imagine if a task required 792 people to touch it. Well, if they're not each doing their task at an exact moment, it's just going to take forever.
Got it. Okay. And then how do you design something in a new way for super low latency? Like what does one have to do today that people weren't doing in the past?
I mean, really, you just have to redo the entire stack from scratch. You can't look. The biggest problem is everyone's trying to solve AI compute with features rather than products. They're like, oh, I've come up with this one change to one portion of that entire forwardly integrated stack, and that's my advantage. And now come write software for me. Come build networking around me. Come build a system for me. Come like bring all your frameworks and get them. And no one wants to do that because it's just too high of a cost for too little of gain. And so in our case, what we did was we just made it completely compatible with PyTorch, which is what everyone develops in. So
Yeah.
you have a PyTorch model, it just works on our hardware. There's no effort required. And because of that, what it means is, and also our API is compatible with OpenAI, so you just change to point to Groq. And
So basically,
that
people have already written this code; it just works, so they don't have to like redo it or something. So you've kind of already can bring in the developers immediately.
exactly. And so we actually went viral. Actually, it's been almost a month right now. We already have 70,000 developers.
Wow.
And for comparison, it took NVIDIA about, I think it was 7 years to get to 100,000 developers. We're on track to get there in 7 weeks.
Wow. Now, people often, it doesn't seem like Apple is usually in these conversations about generative AI, but they have this advantage, or maybe you think it's advantage, or maybe you think it's a disadvantage that they have their own chips, they design their own chips. Like, where do you think, are you like bullish or bearish on Apple?
I'm bullish, but because I'm bearish.
Okay.
So I think Apple is so far behind everyone else, it's going to embolden them to make some smart decisions. They're actually going to partner with others. They're going to do things. Whereas I think some of the more leading, like I think Google has it the hardest because Google's so far ahead of most others that it's hard for them
They
to
have their
recognize.
own chips, they have their own software, they have their own, all this other types of things.
I mean, they wrote the "Attention is all you need" paper, right? Like they're so far ahead. And what they're not realizing is that their strategy isn't working and they need to do some other things. I would say same for some of the other hyperscalers. I mean, frankly, all of them. I actually, this is going to sound a little weird. I think Apple has the best advantage because they're probably the only ones who realize that they haven't locked it down. I think Microsoft, I think Meta, I think Google, all think that they're like the winners at this point.
Amazon, obviously, in there.
Based on what they're doing, based on conversations. But I would say Amazon realizes they're a little behind, and I think that's going to give them a little more flexibility. And you see this all the time. The folks who are the most behind sometimes end up getting ahead of everyone else because they don't find what they're doing that precious, and they're willing to, like Apple just canned their self-driving team and said, you are now working on generative AI.
Yep. Now in the past, like the biggest expense for innovation was like salaries of engineers. And potentially in the future, the biggest expense is going to be this kind of like hardware plus infrastructure. Like, how does that change the industry?
Yeah, in fact, this is a little bit of why Groq got started, because we want to preserve human agency in the age of AI. And the concern is that if a small group of people has all of the compute, then they will have all the say.
Yeah.
And we want to make sure that everyone gets access to compute. So this is a real concern because you will be able to make your employees and your partners and everyone else more efficient by giving them more compute. This is not like search. With search, which is an information age technology, you build your index, and then that index is retrieved on. You can improve the quality a little bit by searching deeper in the index, but it's not a game changer in terms of quality. And so you're building that index for everyone, and they all get the same index. Now, with LLMs, you're probably building that model for everyone because it costs so much to build. But actually, the more compute you give, the better the results get. Think about it this way.
How linear is that? Like, to get 2x the results, do you have to give 100x computer? Like, how does that work?
I don't know that that's well established yet, but let me also put it another way. If you were going to work with a consultant and one consultant was 10% better than this other consultant, would you only pay 10% more?
I'd pay more than 10% more.
And that's generally true of cognitive tasks. And so even if it gets super linearly more expensive, you're going to want that better result because you're probably banking a lot on it. You're going to be making some strategic decisions. And so it really can have an outsized return.
And do you think it will be in the chips world, there are these there's a small number of super expensive chips out there. Some of them maybe going to your phone. Some of them are these, let's say even the GPUs or whatever it might be that are out there. And then there's a very large number of chips, many of which were made, even 20, 30 years ago. And that's the vast majority of things. Are we going to see something similar where you're going to bifurcate and these models will be used, these small for these very, very important questions I can use, but then I'll use this super cheap, models over here for other stuff? Or how do you think people are going to be using these things?
I definitely believe that more difficult questions will get more compute applied to them.
Yeah.
And easier questions will have less compute applied to them. And the way that this is going to work is a lot like playing chess. So when you play chess, you can play speed chess or you can play, normal chess where you think a lot.
Mm-hmm.
But it takes a lot longer. And if you are charged by the second for the hardware, which is effectively what you are, then you're going to want to do speed chess wherever you can. You're going to want to just go with the stream of consciousness output of the tokens, and you're not going to want to have it think really deeply and try and come up with a better answer. There's also an element of, as you were alluding to, smaller and larger models. And that has an effect on the cost and the quality as well. But what bigger models do is bigger models actually improve the intuition of the models. And so even if you run a smaller model, if you run more compute on it, if you have it search deeper, you can end up sometimes getting better answers. And so for some tasks, you may want a smaller model that has all of the, especially if it's an area you've never tried to answer something in before, you don't really need a large model. What you really need is a lot more of those compute cycles to figure out the answer. But then there's another side to this, which is the larger the model, the fewer hallucinations you get. And the reason that happens is, have you ever gone somewhere and you're like, gosh, I think I drove to the GPS took me here. This is not where I meant to go. Have you ever had that experience?
Mm-hmm.
And it's because there was just some extra information unrelated to driving about the neighborhood, about where you were intending to go. And you're like, this is wrong. Well, the bigger the model, the higher dimensional, the harder it is to have one of those mistakes. And so you're probably for a while going to see these models continuing to get larger in order to reduce the probability of these hallucinations. And so for anything where you need to reduce hallucinations, that'll be the way. But you can also do that by applying more compute. It just takes work and effort. And so
why does the compute reduce the hallucinations?
I'll give you an example. What is the next word that I'm about to
say?
Okay, everyone listening to this had the same word in their head.
Yep.
Now, if I were to ask you, or if I asked you to complete this sentence, the second derivative of the square of the hyperbolic tangent is?
I don't know. Right.
So, you don't know.
Okay, right.
So how is it that you don't know?
Because it's not a common thing that people talk about all the time.
Well, large language models are a lot like playing chess. There's a sequence of tokens instead of a sequence of moves. And there's what happens is at each point, the model assigns a probability distribution across all the potential tokens and then sorts them into highest probability first and lowest probability last.
And everyone listening to this is familiar with an autocomplete or something, right?
Yeah. Yeah. And then typically the algorithm will pick one of the top tokens. It doesn't always pick the top one because there's reasons why you don't want to always just pick the most obvious answer, but it goes up here. Now, when you do that, it's like playing the first move that comes to mind when you're playing chess. But if you think about it a little bit and you play out one of those games a little bit, you end up coming up with better moves. This is like the shoulder hit in the second game of AlphaGo. It was actually a very low ranked move. It was played 1 in 10,000 games. And it was only because the TPUs that it was running on had enough compute to go deeper and find it that it played it out.
Got it. Okay, so that's where the compute comes in.
Because you can search a deeper space, right?
Yeah.
The same is true of these tokens. If I ask you, what is the second derivative of the square of the hyperbolic tangent, and I force you to give an answer, you'll give me gobbledygook.
Yeah.
But if you can go back and try a whole bunch of alternatives, then all of a sudden one of them is going to start to make sense. And sort of like when you hear something that makes sense, like if I told you the answer, you'd say, that sounds right. You may not know, but it sounds right. And that ability to detect a good answer is really what you need in order to be able to search. And so these models are very good at that sort of intuitive part. And then you layer on that search part and they get better. It's called beam search. That's the technique.
Now, your chips are built in the United States. Walk us through like the economic advantage. Like, why are you doing that?
Well,
besides the fact that you're a patriot, et cetera.
Well, at the time, we made the decision for a lot of reasons. One was there was a little bit of concern about Taiwan at the time. That wasn't the top reason that factored in. The other was we were able to get a better team because they were hungrier for the business to work with us.
Yeah.
And so we work with Global Foundries, and they fab our chips in upstate New York, and they're packaged in Canada, and we build our systems in the U.S. as well. So we're trying to do this fully North American supply chain. And the advantage here, and why I would recommend that everyone else do this, especially if you're starting to come up and trying to become a successful entity, it's not about being the solution if something happens. It's something could happen, and if I work with you, then I don't have to worry about that eventuality, right? Like I reduce my risks.
Yeah.
There's also it's easier because everyone's in the same time zones. Within
you can iterate faster. If you're going like zero, like in some ways, like a 1 to n makes a lot more sense to do something that's 10,000 miles away, but a 0 to 1, you're going to want it as close as possible.
Yeah, and on top of that, there is an element right now of concern geopolitically. This wasn't the case at the time, that people are playing chess here on this, and most supply chains are stretched across so many different countries. Any one of those countries could just veto your supply chain. And that's a huge risk.
Also, it seems like a lot of these big chip designers are competing essentially to get slots for TSMC to manufacture them. And so they're kind of like bidding up each other to get the slot, or using their own leverage to get there. And I assume that means like the TSMC only has a certain amount of capacity. So it means there's going to be winners and losers there.
To some extent, although TSMC is not the bottleneck for anyone. And it's actually, it's not the GPU, or in our case, LPU itself, that's the limiter. It's this technology called HBM. And HBM is the memory that is used in GPUs.
And what is that's a new term for me. What does HBM stand for?
It stands for high bandwidth memory.
Okay.
And pretty much the entire world supply of HBM comes out of Korea. The two major manufacturers are SK Hynix and Samsung. Now, Micron in the US would love to become a manufacturer of scale for that, but they're generally considered the distant number 3. And so what NVIDIA has done, that this brings us into probably a third thing that they've done that's made them very successful, is they're effectively a monopsony, which is the opposite of a monopoly. Instead of being a single seller, you are a single buyer of a lot of the cutting edge parts. And so NVIDIA
they can sign like these long-term deals with like with Samsung and these other kind of companies,
and SK Hynix and all these others, and they buy up all of the supply. But it's not just the HBM; it's also this thing called an interposer or CoWoS, which is what the HBM goes on, which is a limited supply of. And there's also NVIDIA is the largest buyer of supercapacitors in the world. And so they've got a lock on that too. And there's all of these things. And actually, it was interesting. Someone noted the other day to me that AMD had revised their volume projections down. And that's weird because their demand is higher.
Yeah. Because they can't get this stuff.
They can't get this stuff. So they can't actually produce any. So
wow.
It doesn't matter whether you buy a GPU from AMD or NVIDIA, you're really buying the HBM from Samsung or SK Hynix. So one of the things that we did that was very unusual, we from the beginning, and we made actual design decisions on this, we eliminated any of the exotic technology because we knew that we would never be able to get access to this stuff. We knew that there was a point.
You want to build as much commodity stuff as possible that's easy to access.
Correct. In fact, our next generation chip, one version of it actually had HBM in the design. We actually bought $1 million of HBM because you have to buy it way in advance. Mm-hmm. And that was going to be part of the production run. And when I started seeing you have to buy it that far in advance, it's way more expensive than the chips are. I'm just like, veto, no. And so we took it out. And it really didn't add that much for the cost and the risk. And so, but we have a very unusual architecture. GPUs require HBM. They're built around HBM.
Yeah, I mean, your chips are 14 nanometer technology, which is several generations old, but it's still, that in some ways that's a feature, not a bug, right?
And here's the other one. So everyone's focused on flops, which is the amount of compute that each chip is capable of. But actually, the limiter tends to be the interconnect between the chips, not the flops.
Yeah, if you can have faster communication, then it doesn't really matter, right? You can just add them up, right?
And the best way to think about this, the reason that GPUs are so slow versus our LPUs when they're running a large language model is if you need, let's use a car factory as an analogy. If you need 1 million square feet of assembly line space for the cars to be produced, but you only have a warehouse that's about 1/10 of that size, then what happens is you set up the 1/10 of the assembly line that you can fit, you run the cars through, and then you park them in a parking lot, you tear down the assembly line, you set up the next 1/10, and then you run them through again, right?
Yeah.
That's called batching. That's what GPUs do. And that's because they're waiting for that HBM, that high bandwidth memory, to feed them. Because we have this synchronous interconnect and we have hundreds of chips, it's actually like that full assembly line. And so a token is like the car, and it just goes from beginning to end without ever having to wait for a memory load. And so not only did we get rid of the HBM, we actually, and our supply chain issues, we actually made it faster. Now, the concern that most people have, they look at it and they're like, you need 792 chips to do this. Others only need 8. And we're like,
yeah, but they're 1/100th of the price or whatever. Right?
Well, but actually, each chip is only doing a very small part of the computation. So it then moves on very quickly. And it's a little bit like saying, gosh, a factory costs so much. Cars that come out of it must be much more expensive than hand-built cars, right? And that's an intuition thing that people are really struggling with.
Yeah. Okay. Now, a lot of people think we've reached kind of the limits of Moore's law, or we're reaching those limits. Do you agree? And how does that affect things like chip development and some of these other types of things?
Moore's law was an amazing suggestion that we all followed and treated as real and did heroics to keep going. And I think we should tweak the law a little bit so that it can still be true. Instead of it being about shrinking the number of transistors, or shrinking the size of the transistor so you could fit more and being an economic law, I think we should start saying unit volume in 3D of space so that now we can start stacking chips and continue to get that density. And then once we fully fill up, a cube instead of a 2-dimensional space, then we'll find the next loophole in that law to continue the progress. But functionally, it is not done. And what's moved is, instead of it being about the chip itself, it's become about the packaging that the chip is in order to scale that up. And that's sort of the next game that everyone is playing.
Okay, got it. Now, just in general, as a consumer and a user of these LLMs, they do seem like they're improving at a super fast rate. What do you expect to happen, let's say, over the next year?
So I made some predictions at the start of this year. And my top prediction was that by the end of the year, there would be some deployments where there's effectively no hallucination. There's always going to be a hallucination
Yeah.
because you can't be perfect, but like hallucinations in some cases won't be a thing because it will be solved so well. But not that everyone will have access to this, just that it will be considered a solvable problem because someone will have solved it for maybe a higher price, maybe whatever, because they're doing more compute, they've got a bigger model, right? That's going to change things a lot. Now, the big debate is small models.
I mean, already today, like, depending on how you could define the question in a way, you could find the prompt so you can often eliminate the hallucination, right? So if you're a good prompt writer, you can reduce those hallucinations quite a bit.
Well, and then a bunch of people have actually taken to rewriting the prompt into a better prompt and automatically doing that with LLMs because it turns out LLMs are really good prompt engineers themselves.
Okay, yeah, perfect. Yeah, so then there you go. You could make that better as well.
Yeah, so you'll see. Now this is a latency issue because every time you do another step, it delays giving an answer. Now, speaking of our own book, we are much lower latency, so we're a big fan of these sorts of techniques. But they are currently used and they help a lot. In fact, there's a technique called reflection where you just ask the model, "Hey, on this output, how could you have made it better?" Great, now do that. And,
interesting. Okay.
Yeah. And
then do it again, do it again, do it again.
And typically the rule of thumb is every 3 reflections is a model, a sort of a generational model improvement, but it's to the power. So if you want to get 2 generations, it's 9. If you want to get 3 generations, it's 27. This is why you see in a lot of these papers showing state-of-the-art results, they'll have a number in there. I forget what they refer to it as, but it's like shots or whatever. It's like how many iterations, how many shots. Like they do a whole bunch of instances, and then they just improve the results over and over again. So speed really matters for that. But
when you're doing your own prompts, is there something you've done in a way to get better results today?
Yeah, okay. Things that work with people work with LLMs. So you have a few employees. Mm-hmm. Giving a very clear objective is generally very helpful with your employees, right? Yep. So if you say, write a story, it'll write a story, and that's going to disappoint you. But if you say, write a story that is exciting, or if you define what a hero's journey is, which is something where there's tension and there's an obstacle, and then by the end of it, the tension and obstacle that you started with turns out isn't important, and there's a new one that's important. That's kind of the hero's journey arc. Yeah, and you define that, and you say, now make a hero's journey. It'll do that much better. But then also just asking it to do an outline before it gets started, and then having it turn that outline into output, that helps a lot. But just always think, like, what could I do to get a human being to do this better? And that'll help. Just one that helps a lot, asking it to imagine what an answer would look like. And all of a sudden the answers get much better.
Interesting.
And so then I learned
I got to try that with the humans I work with too.
Exactly. So what I was about to say is I learned that with LLMs, and then I backported that to people, and that actually works very well.
Huh. That's interesting. What now you're in a very interesting position as a CEO. Your employees are some of the most like in demand, most aggressively recruited people in the world. Like, how do you run a company when you're in that situation?
We've always been in that situation from the start.
Yeah.
So we're just used to that. And I think you have, again, it goes to Hamilton Helmer's 7 powers. If you focus purely on economics and it's a commodity thing, and it's like, I'm going to pay you more, you're going to lose. So one thing is, anyone that we hire, we always try and be lower than the highest offer that they get elsewhere. Because otherwise, we don't have enough signal that they're not
Yes,
going to
you don't want the mercenary. You want the person who really believes in what you're doing.
exactly. The next thing up is by having really great talent, people generally want to stick around really great talent. And we have a level of talent, like I think everyone thinks that their talent is great. I remember talking to the CEO who's particularly proud of their talent density. And then they had an opportunity to meet some of our people, and they're like, I thought I knew what talent density was. Now I know, right? Like, and when you just hire really amazing people, other really amazing people want to work with other really amazing people, and it's really hard to pull them away.
But one of the interesting in your world is that the market rate for these employees has gone up dramatically over the last, let's say, 7 years. It's probably gone up like over 20% a year every year. And it's probably the fastest, whereas like the average software engineer, at least in the last 3 years, I believe it's gone down in the last 3 years. Like most of these, more AI related engineers, like so you've got to, you still have to, even if they're willing to take a reduced salary to come work for you, you still have to do some sort of raises and match it over time too, right?
Well, the other thing is we don't do AI. We're picks and shovels.
Right. Good
So
point.
we actually have very few people who actually do AI at Groq.
Okay, so you're more competing with like the NVIDIA or these other types of places. Okay,
that's right.
Yeah.
And
okay,
so,
got it. Okay, so
and we do have people here, but one of the opportunities is when you're near this stuff and you're helping everyone get it to work, you get to learn. And so if you come in as a software engineer or whatever, you get to, or hardware engineer, you get to interface with this in a way that you wouldn't otherwise, because we actually get to work with the best of the best as users and customers of our stuff. And we might actually have more of a front row seat to what matters to them and what that engineering looks like than a lot of others. But we're not the ones doing it ourselves. And so that takes a lot of the competitive pressure off.
All right, two last questions we ask all of our guests. First is, what is a conspiracy theory that you believe?
I am the world's worst conspiracy theory believer.
I would have thought you'd be pretty good at it. Yeah.
So the thing about conspiracy theories is most people who are conspiracy theory junkies, they can believe two things that are incongruent.
Yeah.
And one of the things that I do and that we hire for at Groq is what we call reality quotient. And we've got a whole bunch of like levels of how you improve on reality quotient. But the start is what we call a malleable mindset, or when the facts change, your mind changes. And that doesn't work well with conspiracy theories, because conspiracy theories get debunked and then you're like, oh, I was wrong. But yeah, I would say it's more that I have some weird beliefs and we have some weird beliefs that have come true. But I don't know that they'd be conspiracies. And one of them, shockingly, was that we thought it was obvious that inference would start to become a bigger part of the market. And everyone thought that we were nuts. It's going to be training. And we're like, but you spend money on training and you make money on inference. Of course, inference is going to get larger. I don't know. Yeah. I'm bad at conspiracy theories. I'm sorry.
Okay. Well, that's great. Last question we ask all of our guests. What conventional wisdom or advice do you think is generally bad advice?
I hate giving advice because people don't like to take advice. And so what I will say is, the thing that has been most advantageous for myself and others that I've known is to try and be more fearless. And the problem is not being more fearless, it's recognizing that you've become afraid and that's what's stopping you. I'm in meetings all the time where someone says, we shouldn't do this for this reason. But the reality is they don't want to do it because they're afraid. There are also groups of people who have no fear and get in trouble all the time.
Yeah.
But the sort of folks that you and I interact with a lot are the kind who are more afraid. And so what I would do
is that true, or because like you would think like maybe a typical founder personality might.
a founder is less afraid, but I mean, like in our, engineering, because if you make a mistake, and so you're more cautious, you want to get it all right.
Yeah.
But this is sort of like a Nassim Talebism of, the cost of the risk, or the value of the risk isn't really priced in on high risk things. And so you should really be going after higher risk things, because on the low risk things in life, that real risk that's under there for everything isn't priced in. As an example I like to give is, everyone has to have fire insurance on any property that they rent or whatever, but no one needs pandemic insurance. Yet over the last 200 years, the average person working in an office building has been out of an office more often because of pandemics than because of fires for buildings. So, you got to look at things that are riskier and do those, because then the price to value is a little better. Like startups are one of the best, lowest risk things you can do, because if you're in a big company, you could be in a layoff.
Yep. And you don't grow as fast, and all these other types of things, right?
So look for the things that everyone else is afraid of. Go do those things. And then all the things that no one else is afraid of, be a little fearful of those. I think that's a Mungerism or Buffettism.
Yeah.
And then you'll be much better off.
Okay. Yeah, that's great. Thank you, Jonathan Ross, for joining us on World of DaaS. This has been really interesting. And by the way, I follow you at Jonathan Ross 321 on Twitter. I definitely encourage our listeners to engage with you there. I learned a ton, so this has been super interesting.
Thanks. And thanks for having me. I appreciate it.
And if you're a super data nerd, go to worldofdaas.com. That's DAAS, worldofdaas.com, and sign up for our weekly Data as a Service news roundup newsletter. Thanks for listening. If you enjoyed this show, consider rating this podcast and leaving a review. For more World of DaaS, and DaaS is DAAS, you can subscribe on Spotify or Apple Podcasts or anywhere you get your podcasts. And also check out YouTube for videos. You can find me at Twitter at Auren, that's AUREN, Auren, and we'd love to hear from you.